Well, it appears no one's showing up for the Zoom meeting today, so I thought I'd go ahead and start lecturing on the material regarding the origins of our solar system. So I'm going to use a PowerPoint from another text that I use over at TCC. It happens to be a good PowerPoint and covers the way I like to cover this origin of the solar system story. So let me share the screen and start with start showing you what I'm talking about. Okay, so there's a big question, and some of this is going to seem a little bit like the version of the Big Bang Theory that I tried to quash it in the very first classes. So just keep that in mind. This is not the Big Bang. This is the origin of our solar system, which probably took place almost 5 billion years ago, leading like 4.96 billion years ago. So what we believe happened was there was this cloud of gas and dust and rocks and minerals. Basically, if you look at a spectrum of our sun, it's an absorption spectrum, which we talked about before. Remember, the fact that it was an absorption spectrum told us that there must be a hot, dense source of heat down below and in our line of sight. And in between that hot, dense source of heat, there was a cooler, lower density gas that was causing the absorption. So that basically told us there was a core and also the photosphere. So if we take that absorption spectrum for the sun, we'll find what elements are present. And not only that, you can find how much of each element is present. And if we imagine the early solar system was a cloud of gas and dust, then that composition of the sun would be essentially the composition of that cloud of gas and dust, because ultimately it did form the sun. That composition is by and large, well, for starters, the sun's like 99.8% of the mass of the solar system. Jupiter, excuse me, Jupiter's about 0.1%, and everything else is all in that little, 0.09% basically. So all the rocks, minerals, and all that stuff. But it turns out when you break that down and all that mass, the vast majority of it's hydrogen and helium. And then the vast majority of what's left is actually what we call volatiles, ices, things that would be gases on the surface of the Earth. And then the last part of that, the smallest part, is really the rocks and minerals and metals. So that's what our solar system nebular cloud would have looked like. You can assume it's roughly spherical in shape. It would have some average random velocity that would basically, our rotation axis, I should say, such that the average random velocity is around that axis. Because of that conservation of momentum and gravity is going to force it into a disk. And we're going to explain how that goes using these series of slides. So the planetary system, for starters, if you want to try to understand it, you've got to understand, or if you want to try to find out what its origin is, you have to understand some things about it. And I want to give you a little bit of the data and things we know about that so that we can make sense of it. So first off, if you were to fly straight above the Earth, let's say above the North Pole roughly, straight up till you get far enough out that you can look back and see the sun and the orbits of Mercury, Venus, Earth, and Mars, then at that level you could actually see all those individual planets, and they would pretty much look like stars, even though we know they don't produce their own light. But when you did that, what you'd realize is that all those planets orbit in the same direction. And not only that, with one exception, they all rotate in the same direction that they orbit. So those are two critical factors that we need to take into account if we're going to try to discern how the solar system was formed. Also, if you flew down from above to where we were looking along the edge or along a plane perpendicular to that previous line, you'd fly down and see that basically the orbits of Earth, Moon, Mercury, or excuse me, Earth, Mercury, Venus, the Sun, Mars, including Jupiter and all those guys, are all essentially within one plane. So that's pretty interesting to note as well, that they don't differ very much from a plane. There are some deviations, of course. Pluto is no longer considered a planet, and it actually has a quite inclined orbital, but the rest of them are all on one plane. So that's another interesting tidbit we should take into account when we're trying to discuss the origins. Also, right in between the orbit of Mars and Jupiter, there's a giant asteroid belt. So it's packed full of what we call asteroids, which are mostly rocky objects. And they're not really densely packed, so everything you've ever seen about an asteroid belt in science fiction movies is almost always wrong. You could, easily fly through the asteroid belt with a very low likelihood of hitting something, but still it exists, and that's another important factor. Now, if you flew again up above the North Pole of the Earth, even farther out, so that you could actually see the orbits of all the planets and maybe even Jupiter, what you'd realize quickly is that the distance from the sun to even Jupiter's orbit is really, really small compared to the distances of all the other orbits of the planets. So really, when you get out far enough to see Jupiter, Saturn, Uranus, and Neptune, you can't make out very easily Mercury, Venus, Earth, or Mars. Jupiter you can, of course it's big, but the other ones is really so close together, relatively speaking, that they sort of blend in with the sun. It'd be hard to see them without blocking out the sun. But when you do this, you see the same thing occurs. Basically, all the planets are orbiting in the same counterclockwise direction as seen from above the North Pole of the Earth. And with one exception, they're all rotating in the same general direction as they orbit. So that, again, is something we need to take into account. Also, at this level, we can maybe even start to realize, there's a distinct difference between Mercury, Venus, Earth, and Mars, and Jupiter, Saturn, Uranus, and Neptune. Those inner planets, Mercury, Venus, Earth, and Mars, are in fact mostly made of rock and metals. If you go to the outer planets, and the inner ones we call terrestrial planets, are I think I heard one time called rocky midgets, which I'm sure is politically incorrect, and I apologize if that's an offensive term. But the outer ones are also considered gas giants. And what that means is they're made of substances that would mostly be gases on the surface of our Earth. And they're way larger. So what we also find out is those inner planets are very small, very rocky, and have few, if any, moons. Those outer planets are very large, and very gassy. Sorry, I'm still in third grade. Very gassy, and have lots of moons. Not only that, they all have rings. That's interesting. I know everybody knows that Saturn has rings, but you actually find out that Jupiter has rings, Neptune has rings, and Uranus has rings. Sorry, I keep laughing. Anyways, outside of that is something called the Kuiper Belt. And the Kuiper Belt is basically a little less flat than the asteroid belt, maybe, but still pretty much a collection of objects that are outside of those orbits of Neptune and Uranus and stuff of that sort. And they're mostly cometary stuff. So they'd be comets, and that would be stuff that's mostly made of ices as opposed to rocks. That being said, there's some rocks in them, just like there's some ices in the asteroids. But I sort of picture them as like that dirty snow you get built up around your wheel well in a winter storm as you're driving your car around. That black and sooty, messy ice stuff. That's sort of what's the contents of the Kuiper Belt. And Pluto, in fact, orbits well within that Kuiper Belt. And in fact, that's the reason that it ultimately was demoted from a planet. The rules that they made were, one, it has to be massive enough to have formed into basically a sphere. So what happens is when you get enough mass, you become molten, and when you become molten, then that allows only the uniform or uniformly directional gravitational force, what we call a central force, to shape it. And that natural occurring shape for something by gravity is in fact do to creates a sphere, excuse me. So that actually would create a sphere. And if you get that massive, then yes, you're going to become molten, and then the gravitational force is going to pull equally strong on any given radius r, and any other radius r is going to pull a slightly different amount of strength, so it ultimately forms an object that is spherical. So Pluto definitely met that category. The second one is that it has to order the sun, and I'm probably putting these out of order, but it has to order a star, or excuse me, orbit a star. So obviously Pluto meets that. And the third one, this was the one that kicked Pluto out, was that it had to be massive enough to clear its own orbit. The fact that Pluto is in fact deep within the Kuiper belt tells you that it has not cleared its orbit. It's still being bombarded at every pass due to all the stuff in its orbit. And it actually, just for the record, its orbit actually crosses the orbit of Neptune, but they're in a asynchronous type of orbit, so that Pluto and Neptune are never at the same part of the orbit at the same time, so they're never going to collide. So that's some of the information we get when we just look at our solar system from above. Basically, like I said, everything orbits and rotates, with two exceptions on the rotation. Everything orbits in the same direction and in the same plane. There's this cool asteroid belt. There's this Kuiper belt. The inner planets are made of rock and metals. The outer planets are made of gases. The inner planets have very few moons, and the outer planets have tons of moons and even rings. So that's some of the stuff we're going to go into it with. With that being said, let me flip to the next slide, which I don't know why it's not doing that. But there we go. Okay. So the nebular hypothesis is what we're using here. And basically, again, I told you it started off as a nebular cloud. What we call a nebula is basically the birthplace of stars. And in fact, we'll later learn that the birthplace of stars tends to make groups of stars as opposed to a single star with a bunch of objects around it. But in this case, it was a rotating cloud of interstellar gas and dust and rock and mineral and all that sort of stuff. And over time, gravity and conservation of momentum is going to act. And gravity, having the center being sort of the most densely populated area, that's ultimately going to become the sun. It's now a protostellar sun, which means basically it's not quite hot enough for nuclear fusion to occur at the core. It's got to reach that critical 10 million Kelvin to do that. But it's not quite there yet, so it's a protostar. And that protostar, there's also, that's going to be the center of gravity, the center of energy in some sense. So everything's being attracted that way towards it in that sphere. Well, as you go along that, average rotation axis of that cloud, as you go perpendicular to that, what you're going to see is the objects are migrating from the outside edges. Whoa. From the outside edges inward. This is perpendicular to the rotation axis. The rotation axis would be like this. So they're going this way. Well, when they do that, basically conservation of momentum says angular momentum is made up of a couple things. It's made up of mass. It's made of distance away from the center of the orbit, or the motion, in other words. And it's made of how fast it goes around. And conservation means that those three quantities multiplied in some special way to make out the formula is always going to be the same. So if the distance away goes down, something else has got to speed up or increase, and that's basically the speed. It can't necessarily change its mass, so it's going to speed up, just like a ice skater when she's spinning with her arms out. As she brings her arms in, she starts to speed up, because again, one of the variables went down, i.e. the R for her arms went down, and to compensate for it, the omega, which is the angular speed, had to increase. So there is some resistance to things collapsing this way, but there's no resistance to things collapsing this way. Remember, this thing's going to be a giant sphere initially, and it goes to collapse this way just due to gravity. So slowly it will flatten out, not unlike a pizza dough that's initially a ball, and you take and you throw it up in the air and spin it. It flattens out into pizza. So it's sort of like that. We know this is a reasonable hypothesis because we see various other objects, star building clouds, doing exactly the same thing. That's a photo of one right there on the left. Basically a star just ignited probably, and you see the dust of the disk. That's the protostellar disk, and you can see that's where the planets would ultimately form and stuff of that sort. So we have a lot of evidence that this is occurring. We'll see later on that we have other evidence too. You can see where the gravitate are basically looking at the shifts, the Doppler shifts and whatnot. You can see that the object that is the star in the system is being orbited by other things, by little dips in their light and stuff of that sort. So the Nebular Hypothesis basically allows us to come up with all these things that we see. For instance, we look and we will see that there's, as I said, comets and asteroids. And the asteroids sometimes are made of rocky material, and the rock material sort of randomly accumulated. So you see, pebbles all stuck in an aggregation of a bigger rock in sort of a random way. That tells you that these things just collided, or accreted is the word we use, and left them stuck together in that way. And other parts you'll see broken off. You'll see a very uniform transition from, say, maybe you're looking up at this corner, it'll be very dense materials, and then as you get further and further down to this corner, it gets very low density materials. That's something that used to be part of a bigger molten object. So like when I said, when Pluto was initially building, it got so hot that it became molten and formed into a sphere. Well, it also does that, it's going to take the most dense substances, and they're going to fall towards the center of the planet, or planetesimal in that case. And if something of that gets broke off later, you'll see an actual rock or boulder or stone that has a fairly ordered density. So that's another type of thing that we can see. So the protostar is a large ball of gas, not hot enough to be a star. Like I said, the core's got to reach a temperature about 10 million Kelvin before you can force two protons to run into each other close enough that basically what's going to happen is one's going to spontaneously become a neutron, and some other particles will be spit out. Once that can happen efficiently, which is around 10 million Kelvin, then you actually go from being a protostar to a star. There's a protoplanetary disk. That's the materials that, in some cases, there will be dense areas, and those dense areas can attract other objects to it. Once they get roughly a kilometer in diameter, they'll start attracting other things through the gravitational force, as well as just running into them in their orbit, and they'll slowly build up into planets. The rest of the mass, other than that 99.8%, is basically the protoplanetary disk. That's going to make up all the planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. All the Plutoids, or what we also call dwarf planets, which would be Ceres, and I think we did get Sedna was one, and also of course Pluto. Also all the asteroids in the asteroid belt, all the comets in the Kuiper belt, and all the asteroids and comets in the Oort cloud, and all that stuff. All that other 0.2% is in that protoplanetary disk. So here's the picture of it being initially a sphere, and like I said, or spherical roughly. And like I said, there will be an average random rotation axis, just because it is random. That's the nature of it. And then slowly it'll flatten out to a disk. There'll still be a lot of gas and dust around as well, but that's still trying to fall parallel to the rotation axis, up and down. And the perpendicular to the rotation axis, of course, is going to be altered by conservation of angular momentum. So again, that's how the ice skater spins. When she's spinning with her arms extended, she spins kind of slowly. As she brings her arms in, the part of that R in the angular momentum will actually go down, and that means one of the other factors has to go up. So let me share my screen with you let me stop sharing the screen for a second, and I'm going to show you a different view on the camera so you get an idea of what I'm talking about. So what we're talking about here is angular momentum, which is a quantity called that we label by I. Let me see. There you go. I wanted to make sure my screen was center. So the angular momentum we use the symbol I for. And for a planet, basically, it's the distance it is away, R, times the mass of the planet, and then times v, how fast it's going in the orbit. So that's essentially what we're talking about. There's some other issues, like there's a moment of, or there's inertia related to it rotating as well, but for it going around the orbit, it's essentially this. As you see, if this quantity goes down, since this quantity has to be fixed, so maybe the number is 1,000. So you could have 10, 10, and 10, and that would be acceptable because it equals 1,000. Well, we got to keep that equal to 1,000. So if you drop the radius down to 5, well, now you have, you still need another factor of 20 to get to 100, and then another factor of 10 to get to 1,000. So you might say, well, the mass can't change, so I'll leave that as 10. So I got to account for that by making 20. So you see that the radius went down by a factor of 2, which caused the velocity to go up by a factor of 2. That's how these conservation laws work. If you talk about conservation of kinetic energy, conservation of momentum, something's got to give. And in this case, angular momentum, when the r decreases by a factor of 2, the velocity that the thing is orbiting with will increase by a factor of 2. So I just wanted to give you an idea of that. Again, these are not equations that I require my students to know. I just wanted you to understand mathematically how that plays out. So now I'm going to share my screen again, back with the slides. And I'm going to try to turn it on full screen again, which it looks like I have. Okay, it looks like everybody should be seeing this. So the collapsed perpendicular rotation axis cancels out because of the angular momentum issues, but not parallel to it. Most of the gas lands on the accretion disk, which continues the rotation. Accretion is the growth by material falling inward. So slowly all that material falling inward to the clumpy spots will form the planetesimals and all that good stuff. Well, within the disk, the small particles will collide and stick, and the small particles are blown into larger ones by gas motions, and this leads to larger particles called planetesimals, which is basically what they become once they reach about a kilometer in size. So as the size, gravity takes over and the planetesimals combine to form planets. Today's remaining planetesimals are asteroids and comets. So if we want to look and test our hypothesis about what the sun is made of versus what the nebular cloud is made of, then what we're going to look at is asteroids and comets and find their composition. And that's one of the reasons we study it. Plus, by analyzing these asteroids and comets, we can actually date them using radiological nuclei, and from that figure out how old they are, and that would give us the age of our solar system. So that's kind of interesting. The disk heats up because gravitational energy of the material falling into it is converted into heat energy. Remember, heat, temperature basically, is just a measure of the average random kinetic energy of the molecules and atoms in the substance. So when gravity pulls things inward, they're losing their potential energy, but gaining kinetic energy. They're gaining energy of motion. And then when they collide with other things, all the atoms and molecules in there suffer a net increase in average velocity. Once that's all averaged out, that's officially now an increase in temperature. So obviously the individual thing coming in, the individual chunk of matter coming in with kinetic energy is not an increase in temperature, but once that collides and causes other things to speed up due to other collisions, once you've got a net effect of the total kinetic energy average being higher, then you've converted the gravitational potential energy into temperature increase, which is, heat. The greater gravitational energy converted to heat in the inner disk material than the outer disk, and the inner disk is closer to the protostar, which heats up the surrounding material. And this is sort of critical. I'm going to show you a drawing again. Your book didn't really do it, but I'm going to show you a drawing. So I'm going to stop my screen share and go back to here. So if you made a plot of temperature versus distance within the protostellar cloud, okay, what you'd find, this is the distance from what would be our protostar and what will ultimately become our sun. What you'll see is the temperature falls off like this. We just know this from basic thermodynamics. We know that's exactly how temperatures related to distance. You've experienced it by being near a bonfire when maybe for us guys, it heated up my jeans so much that my leg hair started melting. And then when I moved away, I increased the distance, the temperature got a little lower. So that's the same thing that's going on here. What's critical is remember, the vast majority, other than the hydrogen and helium, the vast majority of what's left is basically those ices and gases and stuff like that. Well, in order for something to actually form a planetesimal, it has to at least be in the liquid state, but maybe even in the solid state. The reason why is in the gaseous state, the atoms and molecules are moving way too fast for gravity to pull them together. So if you get them down to a liquid state, the atoms and molecules are moving a lot slower, and they can be attracted to one another and form planetesimals and stuff of that sort. Well, the problem is the metal oxides like we find in Mercury, and the metallic iron and nickel and the silicates that we all find in Mercury, they have basically temperatures at which they become a liquid around 1500 Kelvin. So this is temperature in Kelvin, by the way. Okay. They have temperatures around 1500 Kelvin at which they become a liquid. That's the metal oxides, which I'll just abbreviate MO for metal oxides. Around 1300, we end up getting iron and nickel. Iron and nickel condense out, in other words, go from at least to a liquid state. They're called refractory materials, by the way, because they're not easily turned into gas. And then the silicates around 1200. Well, these are things that we find in Mercury, okay? We find them in all the planets, in fact, but Mercury has a lot of them. And it turns out if you do this, that tells you what the temperature is. And now if I go down, I can find out what distance this material, which as I said was silicates, so I'll just put Si, silicates are in liquid state at least. Well, when you find out this, you find out, lo and behold, here's the radius of the orbit of Mercury. So this is completely consistent with our hypothesis because now we know, well, Mercury is made of metal oxides, iron, nickel, and silicates. And that's because that's the only things available at this close of a distance. If you want to go to feldspars, well, feldspars don't actually reach that critical temperature or that state in which they're liquid, or at least a liquid but a solid, is around 900 Kelvin, or excuse me, 900 to 1,000 roughly. So when you do that, you find out that's just inside of the orbit of Venus. So now we're already making predictions. We're saying, okay, well, one by one, any elements I find that are going to condense out at a certain temperature, I can find out at what distance we should see them. Well, what we find out is these refractory materials are that low percentage of that low percentage that was left after we got rid of the hydrogen and helium. So all of a sudden now we start to understand why the inner planets are made of minerals, metal oxides, iron, nickel, silicates, feldspars, trollite, and stuff of that sort. When you get to the actual water ice, which is one of the major components in the protostellar cloud, that's only going to condense out at around 175 Kelvin. And lo and behold, that's just inside of the orbit of Jupiter. So these inner planets, one, are small because they had only access to these rare things in the nebular cloud. And these outer planets are large because they had access to all these rare things, but they also had access to water and ammonia water ice and methane water ice and argon neon ice, all these different compounds. So now we even understand basically the sizes of the planets as well. So we've got their composition made out, we've got their sizes made out, all from this understanding of how temperature is related to distance around the protostellar cloud. So let me go back to sharing my screen. No, I want that one. Okay, so this is what they're showing in this graph is that, hey, the left-hand side is the protosun, then you got Mercury, Venus, Earth, and Mars, and you see that the refractory materials, which are really difficult to put in the gaseous state, they're available to everybody, right? And you can one by one select which ones and where they condense out. You can select where they'll be found, and then lo and behold, you only see planets having them at a distance further than that, or at least equal to that. Water ice, on the other hand, which is one of the highest prevalence things, as well as all the other highly volatile materials, they don't condense out until they get just inside the orbit of Jupiter. So that explains why Jupiter, Saturn, Uranus, and Neptune are big. They had access to the bulk of that small percentage of material, and also why they're made up of what they are, because they were able to get large enough to not only attract all that water ice and other highly volatile materials, but they got big enough, quick enough that they could then attract hydrogen and helium even, and then hold on to them. So they had access not only to that small percentage, but even to some of the hydrogen and helium, which is the huge percentage of the protostellar disk. So this is what this graph is showing, and it helps you sort of make sense of how the planets came out to where they are. Let me advance this slide. So the primary atmosphere. So when these planetesimals first formed, they had gas from the protostellar disk attracted to them, but you know, if the rule of thumb is, at least in astronomy and astrophysics, the rule of thumb is that if your average kinetic energy, or excuse me, your average velocity of your molecules is 1/6 of the escape velocity for the planet, then you're going to lose that substance. So it turns out the primary atmosphere is lost by most things. Obviously, the outer planets, Jupiter and Saturn, for instance, they did not necessarily lose theirs because they got so big that they could actually hold on to hydrogen and helium, which really have the fastest average kinetic energies for a given temperature, because hydrogen is so light and helium is just, you know, moderately heavier. So that's the primary atmosphere is. Most planets, like I said, will tend to lose that because they just don't get massive enough to hold on to those things. And then you'll get a secondary atmosphere that occurs as the molten metals and rocks and minerals are molten. They're going to allow gases to bubble up out of it. And that secondary gas can be part of, or that secondary star, that gas can be part of the primary atmosphere. But as you have like volcanoes and stuff like that, they're going to release even more of it, and that will form the secondary atmosphere. So comets can come in later and bring in other volatiles to the planet, so you can still get some trace elements of things that you wouldn't expect, like water and volatiles on Mercury, Venus, and Earth and Mars, but you'd expect to find them in small amounts because they could only come by comets or things like that. So obviously the big question is, how the heck did we get, you know, 2/3 of the surface of the Earth covered with water? And the current hypothesis is that we were hit by a comet, and the comet brought us a good deal of water. Now, if you think about it, the actual water on the surface of the Earth is still a very small percentage of the mass of the Earth, but it's a large percentage of the surface area, but it's still very, very shallow. It's not even, you know, not even past the crust. For instance, the depth of the ocean is not even as deep as the crust is. So it's not that much water, but yeah, that's our working hypothesis. It's approaching a full-blown theory that basically a comet delivered water to the Earth. We did some experiments. We discovered, for instance, or I should say experiments, we did some observations and collected water that was found in comets, and lo and behold, we found that water in comets had exactly the same isotope ratio as the water on Earth. So we were like really confident, yes, we're on it. And then we found other comets that had entirely different isotope ratios. So it seems that some isotope ratios are different than others in comets, and maybe that one type of comet that had the water with R ratios was the type that hit Earth. So within 5 astronomical units of the sun, the planetesimals were rock and metal. These give rise to the terrestrial planets. Earth and Venus may have had primary atmosphere, but soon lost them. Mercury has no significant secondary atmosphere. Venus, Earth, and Mars all have substantial secondary atmospheres. Mars is a really wispy atmosphere, but still it's significant compared to Mercury or even our moon. By the way, our moon, which is a rarity, and of course Mars has a moon as well, which is also a rarity. In the case of our moon, we believe that was a basically a thing about the size of Mars hit us early in the period of heavy bombardment, basically when that protostellar disk was shrinking to a disk instead of a ball. There was a period called the heavy bombardment where everything was getting hit at all times. We think maybe something about the size of Mars hit us, shook off our outer layers, and then what was left was orbiting us as like a ring system, ultimately accreted into our moon. And that was actually driven home to us when we finally made missions to the moon and found out the composition of the moon was very much like our crust. So that's kind of interesting. In fact, also Charles Darwin's grandson, if I remember, no, his son, Charles Darwin, actually did a calculation of the orbit of the moon and realized that the orbit of the moon used to be a lot smaller and that it's slowly drifting away from us. If you run the clock backwards, that tells you that the moon used to be the same place the Earth is. So that's also consistent with it. So the formation of our solar system led to the gas giants. Further from the sun, planetesimals could contain volatile and organic materials. Many accretion disks formed around these large planetesimals. That would be their rings, basically, and began funneling material onto them. Gravitational energy was converted into thermal energy, which heated the planets. So like I said, the moon's a natural satellite of a planet or asteroid, sometimes formed an accretion disk. Yes, we actually have some asteroids and comets that have their own moons. Kind of interesting. You'll find some photos of those later on. Dwarf planets are round objects that orbit the sun but have not cleared their orbits of smaller bodies. That's what we also conveniently termed Plutoids to pay some homage to Pluto. Asteroids are the small bodies found inside Jupiter's orbit, and comet nuclei are the icy planetesimals in the outer solar system that survive the accretion. So when we look at other star systems, we find that is actually common. So we put a disk up to it to actually block the view of the star in the system, which is really, really bright. And then lo and behold, you can see this nice gassy dust, gas and dust disk in a plane. So that's some of the evidence again. To date, we found, and I think it's even quite a bit higher than this. I think we're over 5,000 now, 4,000 extrasolar planets or exoplanets since 1995. We're actually finding them, a Kepler telescope's finding a ton of those now. We found them several ways. We found them from the radial velocity method, the transit method, microlensing method, direct imaging, and astrometry. So we're going to go over these a little bit. So the radial velocity method, basically, if you look at a Doppler shift, or if you look at spectra of a particular star, what you'll see is the star comes towards us and away from us, towards us and away from us, towards us and away from us. That gives us an idea that it's obviously orbiting. Even the case of our sun and Jupiter being really teeny compared to the sun, still pulls on the sun pretty appreciably. So the sun wobbles back and forth. So when we see this wobbling, we think, oh, well, there's something orbiting it, and that gives us some way of detecting that there's planets, planetesimals, large objects or whatever orbiting the sun, because the sun has to orbit in response as well. If you see multiple humps and things, you can start counting the individual planets. So that's the radial velocity method. There's a transit method that only occurs if the planet actually goes in front of and behind the star. So we actually have to be in the orbital plane of the planet to do that. But if we're lucky enough, we can see every time the planet goes in front of the sun's brightness will decrease, or the star, I should say. The star's brightness will decrease. And each time it does it, it'll decrease probably by a different amount unless the planets happen to have the exact same sizes, which is very unlikely. Not only that, when you well, in principle, when the planet gets around the other side, but before going behind the moon, behind the star, then the planet can actually provide additional light. So you could even get a dip as a result of the planet going behind the star too. Usually it's insignificant though compared to the actual starlight. So that's the transit method. Direct imaging, if we actually are lucky enough to have a powerful telescope that can see that well, then we could actually take a picture of the planet. It's very hard to do that. Stars are much brighter than planets. You got to block them out, all that stuff. Microlensing is a neat way where basically you use the gravity of a star or a nearby object to sort of magnify the image of something in the background. So you're basically using general relativity and gravitational lensing. And then astrometry detects planets by precisely measuring the change in position of a star. So if you are able to measure the individual change in position, you can see that it is in fact wobbling. When we first started finding planets, the first thing we started finding was hot Jupiters. Well, you get the idea that, oh wow, the universe is packed full of hot Jupiters, meaning objects the size of Jupiter but that are really close to our sun. Well, it's sort of like throwing a fishing net out, and the fishing net has 4-inch holes in it, and you catch all these fish, and like 99.99% of them are 5, 6, 7, 8 inches. In other words, 99.99% of them are bigger than 4 inches. So you might conclude, wow, the ocean's just packed full of things bigger than 4 inches. But what happened was you just had holes that let all the other ones loose. Well, that was what's going on with this. Our initial methods were only capable of detecting the heaviest planets that were closest to the star because they would make the biggest effect. It turns out there are a lot of hot Jupiters, but they're not necessarily the predominant type of planets that we see. But it is weird because when you have a hot Jupiter, that suggests something was able to accrete a large percentage of mass of various masses and get large enough, even though we expect most nebular clouds to be mostly hydrogen, helium, and then those volatiles. So it's still a mystery. We have ideas thinking that maybe they migrate, all sorts of neat things about, you know, slow loss of orbital energy, then they'd slowly migrate inward. But the jury's still somewhat out on actually what causes those. So most planetary systems found to date do not resemble ours. Researchers have also found many Neptunes and super Earths. Planet locations, orbital inclination angles, and orbital directions are different from our solar system. So there's a lot of different scenarios of star systems / solar systems, and they don't always look like ours. We're left with our origin story of trying to explain ultimately how did those rarities occur. For instance, remember I told you Jupiter, or I told you that one planet didn't orbit or didn't rotate the same direction that it orbited, and then another one didn't in the gas giants. Well, it turns out Venus does in fact orbit in the opposite direction, and it's so slowly that a day is longer than a year on Venus. We think that was due to a collision that literally hit it so hard it turned it spinning backwards. Another thing is Uranus is actually its rotation axis is almost parallel to the plane of its orbit, so it just sort of orbits or rotates perpendicular to everything else. That again we think was due to a collision. I would have suspected it occurred obviously in the heavy bombardment before it was that huge, because what could be so big to make make Uranus trip over, but here we are. So that is what we find to date about the planetary systems. They are very different than ours. We see some similarities, but some differences, and we just use a comparative comparison basically to make sense of them. And that is it. That kills the origin of the solar system portion of this course, and this will be posted a little later. I'm going to turn the regular camera on instead of the document cam. And since I had a couple people came in after we got started, hey, Haley and Roshana and Anthony was here earlier. You guys have any questions about anything?